We conclude Chapter 2 with 2.7. This is an application of derivatives called marginal analysis. So we recognize a lot of people who take this course are business and econ majors. Not everybody, but a lot of you guys are. And so we really lean towards the business and econ style applications. And this is really our first big one. Okay, so what is marginal analysis? So I'm defining a few things here. We're going to focus on cost, but we will also apply these ideas to revenue and profit. Okay, so, but as it applies to cost, let's say the total cost to produce X units is given by C of X. So maybe, kind of think of like a factory or some kind of large scale production. The total cost to produce your X units, whatever you're making, maybe you're making, DVD players or staplers or who knows what. Okay. Then we've got the exact cost to produce one more unit. So you think, okay, if it's C of X produces X units, then how could we ever tell the cost to produce one more above that? So whatever X is, if you go one more above X. So you would say, well, you would need to find the cost to produce X plus 1 units, and then you subtract the cost to produce X units. And after you subtract, the difference is going to tell you the cost to get that very next one, right? Okay. And then you've got marginal cost. And obviously this is what it's leading to. Marginal cost is defined as C prime of X, the derivative of your cost function. So what is that, and how do these all connect? And here's the idea. Here's how exact cost connects to marginal cost. So it turns out the marginal cost very accurately approximates your exact cost. Okay, so the value of this derivative for a particular X value very closely predicts the exact cost to produce one more unit than that. And we'll see that in a graph after we do an example here. And in fact, let's do it. You might also be wondering, like, why, what's the problem? Why do we need to approximate this? Isn't this, can't we just do that calculation and then we know it exactly? Well, sure, you could. But we really want to see the derivative function, because then it's so much easier to do this sort of calculation for many different X values. And it turns out, well, this might not look like a big deal when you go to like a large scale production. I mean, this approximation is going to be quite good. And it turns out this is just simply easier to work with and easier to compute than having to do, compute both of these values and subtract. Although, for any given X value, it's not difficult to do this. Having, this function defining for the all X values at once, really minimizes the amount of work to see the effect at different X values. Okay, hopefully I'm making the point there. All right, let's see this in an example. Let's go with C of X equals 640 minus 12x plus 0.1x squared. Okay, so there's our cost function. And it's not uncommon for a cost function to be a parabola, have an x squared, right? The idea is there's some x value that will minimize your cost, or perhaps maximize your cost, which you want to avoid. Okay. Let's find, in part A, let's find the exact cost of producing the 501st unit. And that's a bit tiny there, 501st. The exact cost to produce that, just that very last unit, number 501. Okay, so we'll use our formula here, and X will be 500. So we're going to compute C of 501 minus C of 500. When we take that difference, then that will tell us just the cost of that 500 first unit. And again, that's not too hard to do. We can plug 501 into our function. I got 19,728.1. So it's $19,000, $19,728.10 to produce 501 units. Plugging in the 500, 19,640. So 19,640 of that was for the first 500. So how much just for that very last one? Take the difference, 88.1, so $88.10. Whatever, they don't tell us what type of unit this is. Now you might think for a second, isn't it the same cost for each and every unit? I mean, why would some units cost different than others? And yeah, it definitely is the case where not every unit costs the same in a sense. Usually the first few units you produce have this massive, massive cost. So if you were to produce like 10 units, it would be this massive amount of cost because you have to pay your employees, you have to pay for, maybe the rent for the building or for the land where your factory is. You've got to get insurance, right? There's all this overhead. And then you start actually making product. So you could say those first few units are incredibly expensive, but the more you make, then the cheaper it gets. Sometimes there's a point where it turns around, and actually if you start producing too many units, then the cost starts to go back up for each unit as well. So you kind of want to find that sweet spot. Okay, so for number 501 here, we've got $88.10. So what are we going to do next? So part B says find the marginal cost of producing 500. Okay, so we'll do the other side. This is going to be the C prime. So first thing we need, we're going to plug in 500, but we need C prime of x first. So based on C of x, we're going to use our shortcuts for finding the derivative. So we can just go one at a time. Derivative of 604 is 0. Derivative of negative 12x is negative 12. And the derivative of 0.1x squared is 0.2x to the first. We multiply the 2 down, it drops to a first power. There you go. Or if we clean it up a little bit, negative 12 plus 0.2x. Okay. Then, once we have this, we can plug in our 500. And you notice that is a very good approximation of our previous answer. Plugging 500 into this got us 88. So we know that's not the exact cost to produce that 500 first, but it's really close. And that is plenty good enough for us for our purposes, maybe running this factory or running this company. So kind of here's the idea and why this works. Why is that a good approximation is a good question. So I think I will do a short Desmos video at the end of this section to highlight this a little bit better. But I think this drawing does a pretty good job. So in Desmos, I would graph y equals 640 minus 12x plus 0.1x squared. And we'll get this parabola, and that's that curve happening right here. Okay. So that's C of x. All right. Then we could also graph this. So this, I went ahead and found the equation of the tangent line. So here all we did with this, that's the slope of the tangent line. But if we go a couple steps further, we can find the equation of the tangent line. I won't go through those details, but that's what it would be. 88x minus 24,360. So that is this tangent line right here. Okay. Oh, looks like I used the point at 500, 519,640, along with the slope 88. You could get that equation right there. Then you notice there's this other point at 501, 501, 19,728.1. So think of this point here as being the 500, and then 1 unit further, and now we're up here, 501, and there's the 19,728.1 on the C curve, the cost curve. So we go up 1 unit, and then the cost goes up as well. So what is the derivative doing? What is this tangent line doing? So notice our tangent line passes through here at 500. So if we continue that out this way, C prime 500 would be this right there. Just from, let me make it a little bit bolder. That's what we found to be the 88, right? Why would that be the 88? Because that's a slope. So if it goes over 1, it goes up 88. And that's the slope of that tangent line. Or you might say up 88 over 1, right? Rise over run. Or over 1, up 88. So now there's a little error here, right? We're hoping to approximate, the cost of that last unit. Well, the cost of that last unit is that total distance, right? We went over 1 unit. The total distance is the 8810. Well, the tangent line, and it's not to scale, obviously, the tangent line came very close to this number. It should probably actually be like right under it. If we were to draw this more accurately, it would be so close in there, because that was 88, and then there's that last 0.1, that last 10 cents is the gap. And so the derivative value passing through this point, that slope, it turns out, that's a very accurate approximation of that last unit. Okay. This example goes on. We can also talk about average cost. So an average cost is defined as C bar of X, like that. So we put this little bar over the C. And that, to calculate that, you take your original cost and divide it by X. Why would you do that? So here we're thinking not the cost of each individual unit, but the average cost of all of the units. And this is probably how we think of the cost of producing units. We don't think, well, the first few are really expensive, and then as we keep going, they get cheaper. We think, no, they all cost the same amount, but that's thinking in terms of an average. So take all of your costs together, divided by the total number of units, and that's the average cost per unit. So, if it cost, like $19,000 for all of your units together, but you had 500 units, then you could get an average cost per unit like that. Okay. And then we define the marginal average cost. So we'll take the derivative of your average cost, and that's the marginal average cost. By the way, the word marginal, if you're thinking like margin, it's getting the gap. It's a way to get the value of the gap between one value and the next, which is what we saw in the first part of the example, right? And it's an approximation for the cost of that next unit. So think of the margin as like how much you have to jump from one unit to the next. Or here, how much you have to jump from one unit to the next, but thinking in terms of an average cost. So how much would the average cost go up or down from one unit to the next? Okay. Let's continue our example from before, now with average cost and marginal average cost. Find the average cost to produce 500 units. And so we'd say, okay, C bar as just our original C divided by X. always simply divided by x. And then we're going to plug in 500 everywhere. So we plug in 500 there, divide it by 500. Well, we did the numerator already, right? It's the 19,640. When we put 500 in, we divide that by 500. And there you go, $39.28. Now, this is really interesting. A moment ago, we found the 500 first unit to cost over $88, $88.10. But now we're saying, but the average is only $39.28. What's going on? Well, it turns out, somewhere along the way, these items were really cheap. And then, but we kept producing more and more of them. And for whatever reason, the cost per unit was going up. And eventually by 501, it was at $88 or a little more. But for a while there, it was really cheap. So this is the average. There were a lot of units that were, well under even $39. Not that we really have to analyze. They're not asking any of that, of course, but it's good to dive into it. Okay. Well, you know what's coming. Find the marginal average cost at 500 units. Okay, so we want C bar prime 500, the marginal average cost. So we need to find the derivative first, and then we'll plug 500 in. Now this is tricky. How do we find that derivative? Because, that's not a polynomial, right? I mean, we're dividing by x. Okay, so we have to be really careful with this. All right, we'll just kind of state it again. There's the average cost. Here's what we got to do. Split this into 3 separate terms. 640 over x minus 12x over x plus 0.1x squared over x. And then simplify each one. And this is still the average cost. Now we're writing with a negative exponent, x to the negative 1. Here they just cancel, and we get the constant. Here one of them reduces. And we get this, you could call that a simplified version of the average cost, allowing us to now take the derivative. So derivative here, the negative 1 comes down, drops, that becomes a 0. Derivative here is just the 0.1. And you may choose, I like to do this personally, when I'm taking a derivative, you want to have that negative exponent. And if the answer was the derivative, you could just leave it like that. But because I'm about to plug a number in, I prefer to just go ahead and rewrite it as negative 640 over x squared, because it's easier for me to think about plugging a number in that way. Okay, so finally, we'll plug in the 500. And this number right here is what I got, 0.09744. And you see I've got some notes here, and this is our answer. Just that, what's there on top. But what you see around is an interpretation. What does that even mean, 0.09744? The marginal average cost. Okay, so let's think about the units. So what's on top is a dollar amount, and what's on bottom is the number of units. Always remember, derivative is a slope. So think it's like, the change in y over the change in x. So it's the change in the dollar amount divided by the change in the number of units. So if you think of it this way, that many dollars over 1 unit, for 1 more unit, the average cost is going to increase by almost 10 cents. A little under 10 cents, $0.09744. So if we make just 1 more unit, right, we do that 500 first unit, then the average cost of all of the units is going up, which should really tell us maybe we want to consider if we want to keep producing more of these because it's actually getting more expensive per unit as we go. But yeah, you know what? Maybe there's a big demand out there, and we're really pulling in a lot of money, and that's fine. But if not, that's another story. Okay, let's stop this video here. We'll just have one more video to wrap up this section.